Can additive manufacturing aid the production of motors? Amiee Jackson is a researcher at Oak Ridge National Laboratory at work on that question. Here's what she's learning.
Okay, so these components are the rotor of a brushed DC motor. They look different from the conventional ones because they aren't laminated in that they don't have a bunch of sheets stacked on top of each other. They're just solid instead. What we set out to learn here was, can we manufacture the same geometry additively out of the same material, and does it work? So one thing that additive offers is inherent design freedom or geometric design freedom, as opposed to in conventional processes, the need for tooling oftentimes constrains, limits the geometric freedom of design. So using additive to create these reluctance rotors may offer advancements, achievements, untapped spaces of motor performance. So typical rotors are made out of an iron silicon alloy, which is what we used here. We used a 3% silicon alloy. But the thing is that as the percent silicon increases, up to 6% usually, the properties of motor performance also get better, except the property that helps, like ductility, which is what helps you be able to manufacture these sheets, it gets worse. So there's this competing objectives between ductility and the performance of the motor. Additively, we want to be able to produce these motors with that better alloy that has the better magnetic and electrical properties, and not have to care so much about the ductility, which is related to the manufacturability of the component. So the additive manufacturing process we used was powder bed fusion, and the exact machine was a Renishaw. When we tested the rotors, the conventional one performed at a much higher efficiency than the ones that we have printed, in that the ones that we printed required almost 10 times the current that the conventional one. They also had audible losses, and they didn't achieve the speed that the conventional rotor achieved at the same voltage. However, we understand that that's most likely because of eddy current losses or heat losses, or even perhaps losses in the rewinding process that cause more friction between the rotor and the permanent magnet around it. Those eddy current losses are the reason why the conventional rotor has those laminations, is to decrease those. So in the future, what we'd like to do is iterate through different material formulations to increase the efficiency, and at the same time improve process elements to simulate something similar to laminations. One thing we were really concerned about is the magnitude of those eddy current losses as compared to the efficiency of the motor itself. So we didn't know when we printed these if they would spin at all, or if those eddy current losses would be really significant in that, like, you wouldn't be able to run the motor for more than 5 seconds before it got really, really hot. Neither of those things happened. Our motors spin, that's great. And they don't get incredibly hot really quickly. I don't think I've even noticed that they've gotten hot at all in the time that I've ran them. So those two things are promising and good. Eventually, the next step that we'll take is to move to materials that have a higher efficiency, theoretically, for motor applications, and see if we can print those and if we can make them work better.